Okay, well, I'm very pleased to have Caleb Canas here today to talk to us. Caleb is here all week. He's visiting from NASA Goddard, where he has been an NPP postdoctoral fellow since late 2022. He got his PhD in 2022 from Penn State, working with Mahadevan and myself. On HPF, NUID, science, apogee. He is an expert in M-dwarfs and finding planets around M-dwarfs and making fundamental measurements of them. And lately he's been co-leading a very large JWST proposal to do some deep spectroscopy of a variety of M-dwarf targets looking for planet signatures. So I will hand it over to him and say, I'll remind people that if you want to meet with him, his schedule is fairly open this week. And by all means, set up a meeting. He's going to be hanging out in 488 Stewart.
Thanks for the intro, Chad, and thank you for giving me the opportunity to come here and present sort of some of the work I've been doing. And I do want to preface this where I'm hiding some of the work I've done, but it's really enabled by a large group of people. So it's not just me, it's collaborations with people at Goddard, at Penn State, at University of Arizona, Carnegie, and a bunch of other institutions. And so I'm gonna, broadly, it's a talk that's in 3 parts. So one's gonna be a search for these planets using tests. The second bit is going to be briefly talking about a project for obliquities that I have for next that we just got data for this weekend. And then the bulk of this talk will be JWST. And I want to sort of step back and just put this in context, our broad goal of what we're hoping with this sort of multi-pronged approach, sort of looking at this particular class of planet. In this case, these are gas giants orbiting M-dwarfs. And I'll get more into sort of why we're looking at them and why we're particularly interested in a few slides. But first, I just want to say we really want to understand planet formation in the context of our solar system. And so this is a plot of the NASA Exoplanet Archive where I've noted sort of our 2 gas giants, Saturn and Jupiter, as well as everything else that we covered through transits, radial velocities, astrometry, etc. This particular talk is going to focus on sort of that little square in the upper left. So we're looking at short period gas giants. So you can think of roughly periods 1 to 30 days. Masses from 0.2 to 13 Jupiter masses. And that's what is the focus of this talk. But we really want to sort of see how we can take what we know from our solar system, that's well studied, we have sort of some sense for how these planets form from core accretion, and put into context, particularly again, for these planets where we have no analogs in our solar system. So we see this nice little population. Traditionally, that's the hot Jupiter population. I'm particularly interested in zooming in on that section and looking at it from the perspective of the stellar host. So here I'm plotting currently all of the known hot Jupiters in sort of gray. That's again as of probably last week. There are roughly 600 hot Jupiters that are known, where we have masses in period. A lot of them come from ground-based surveys, Kepler, etc. And as of last week, again, we have roughly 30 of these gas giants. So they're effectively analogs of the hot Jupiters. They are, again, periods less than 10 days. Their radii is greater than 8 Earth radii. But these orbit much cooler hosts. So these are M-dwarfs, where the effective temperature is less than 4,000 Kelvin. And this population has slowly grown. In 2018, I believe all we knew were 2. So now we've found 30. So we have a nice little growing sample. And some of the work that we're doing is trying to really increase the sample so that we can have a number where you can then look at bulk properties of these systems, of these planets, and say, how do they compare to the known hot Jupiters? And what can that tell us about how these objects potentially form? What are the similarities, or are there any differences in said population? I do want to step back and motivate why M-dwarfs. And there are 2 main reasons that, I think you've probably heard it as the M-dwarf opportunity. There are many nearby. So we know from recons and other surveys that M-dwarfs are really the most sort of abundant star in our galaxy. So if you're really looking for planets that are potentially rare, we know how Jupiters are rare, we expect their analogs around M-dwarfs to be equally rare, then you really want sort of a large sample. And that's really where M-dwarfs come to shine. These are also smaller in mass and radius compared to, say, a sun-like star. So there's a in this little plot, M-dwarf on the left, sunlight on the right. And that really makes it easy to detect sort of observationally in terms of transits, so your transit depth is deeper. In terms of radial velocities, your semi-amplitude velocity is much larger. So in terms of detectability, they're a lot easier to actually detect. So those are sort of one of the two main reasons we wanted to go after these with the instruments we have available. And again, just doing it back to the subset that I'm looking at here, these are the giant exoplanets around M-dwarf stars. We are sort of using this monitor and not calling them hot Jupiters just because they aren't really hot. So this sample, the hottest object is probably 700 Kelvin. The coolest one currently goes down to like 380 Kelvin. So it's really a different temperature regime than hot Jupiters, which tend to be roughly 1,000 or greater. And especially in the hot Jupiters around flying stars, we see sort of a radius anomaly. We see they're inflated due to ohmic heating. That is not the case for these objects. So these are getting cooler. They're also much more well separated. So the entire population generally is A over R star of 10. So this is a neat sort of, I guess, they are short period, but they're perhaps a bit more analogous to warm Jupiters. And we particularly want to study, these objects because they intrinsically should be rare. So going back to sort of the initial core accretion papers, I think some of the seminal work is like Laughlin et al. 2004. We expect these planets to be rare around M-dwarfs, largely because these are smaller than the sun. So again, masses of M-dwarfs range from 0.1 to 0.6 solar masses. So naturally expect less material in the protoplanetary disk. That intrinsically means there's less stuff for you to actually form cores that can then lead to runaway gas accretion. And the growth of said cores is also slower. So those two factors combined should make these objects rare. And I will note that tests, the sort of current occurrence rate estimates are roughly half of that for FGK dwarfs. So we know they're rare, and that's again sort of why we're looking at a large sample via tests. And I do want to emphasize that some of these planets do sort of represent an extreme end of sort of planet formation. In particular, sort of this is a press release that we had for TI 5205, that it is a 1 Jupiter mass, 1 Jupiter radius planet orbiting a 0.4 mass and radius star, so a mid-M dwarf. It's an M4. That one in particular is very massive for the type of star that we have. And if you sort of just look and estimate how much solid material you need, you can easily exceed what you'd expect for sort of, again, a comparable protoplanetary disk that you measure the mass for. And so these are planets where we're really interested in seeing how do you form something so massive against something that's, again, 0.4 times that, the mass of the sun. We're also interested in sort of not just looking at them individually, but as a whole, sort of what observable imprints do we have for this population? Again, that's motivating why we want to do this as a survey, from photometric perspective to find them, from an RV perspective to get masses, to get sort of system parameters to see if we have any additional companions. So we want to see how do any imprints of migration formation sort of manifest themselves in bulk parameters of the systems, in sort of their architectures. Are they aligned? Are they misaligned? Do they have other companions? And also atmospheric properties. So now with JWST, we can actually start to observe the atmospheres, get a sense for what their composition is, what the abundances are in the atmosphere, and what that can potentially tell us about, again, how these things potentially form. And again, sort of as an overview, this is ongoing work. And so I will get into right now sort of the finding and characterizing gems. And so this is a combination of a radial velocity survey, but also a search in tests. So we're looking at a blind survey of 1 million objects. So effectively a volume limit sample of M-dwarfs within 200 parsecs. I'll briefly mention our search for any misalignment. And so this is through MurinX. So we have an active program this cycle where we just observed the first RM observation of a mid-M dwarf with a gas giant. So that's really exciting for us. And I think a big part of this will be the atmospheric properties. And so particularly diving into the first target, but looking forward as to what we can expect for a large sample there. We have 7 planets where we've observed with JWST. And so we're really excited to see what that can tell us in terms of metallicities, C-to-L ratios, and just overall the atmospheric composition for these gems. I probably won't get too much into the details of the RV, and I'll focus on photometry, but I do want to highlight that our survey has been pretty robust at finding planets, especially since I graduated. We've been working a lot with sort of undergraduates, graduates, and other sort of early career postdoctoral researchers to really sort of take the RVs take the data that we have and put out to the public. Here I'm highlighting a few recent publications. So Andrew Hodzinski recently released 2 super Jupiters. So those are the first 2 gas giants orbiting M-dwarf with masses greater than 5 Jupiter masses. So that recently came out, and it's in press, so it was already accepted. So if you're interested in sort of the massive side of these things, take a look at that paper. Rachel Fernandez is currently putting out a paper for a super Saturn, so something that's slightly larger and more massive than Saturn, orbiting a metal-rich M-dwarf that is currently under review. And then we have a graduate student, Anjali Sandoval, and 2 undergraduates, Shane O'Brien and Amber Wong, who are leading individual papers on 3 other systems. So again, those are all should be coming out really soon. But we are, I think, in terms of as a rate of velocity survey, really leveraging the tools that the community has sort of developed to find these objects, characterize them, confirm them, and have them out to the community so that anyone can follow up on them if they want with JWST or with other instruments. So our photometric survey, searching for gems, we really want to sort of, as I mentioned, develop a population of gems that we can then analyze in detail. As I mentioned, in 2018, there were only 3. As of now, there are 30. We're really aiming for at least roughly 40 gems that have been, really precise masses, really precise radii, before we can start to sort of even investigate any statistical difference between the M-dwarf population and the FGK dwarf population. So that's really the motivation for this component, which is we're taking advantage of TESS and Gaia, so 2 all-sky surveys. TESS has observed millions of M-dwarfs. It really is a wonderful instrument. And Gaia provides us with parallaxes and a bunch of other things with which we can use to sort of really make a volume limited sample of these M-dwarfs. And so we've had that 1 million sample. We are currently analyzing that, at least a subset of that, the 100 parsec sample that I'm going to sort of briefly mention today. This represents a lot of data, and so it's been a lot of work sort of developing the pipeline to do this and developing the tools really to robustly search for things around these M-dwarfs. And to give you context, in TESS, these are still very faint. So we're talking Tmags of anywhere from 13 to like 15, which most tools and most sort of even high-level science products that are already available don't tend to go that faint. So we had to sort of develop some tools to get us where we want and to enable sort of the search. I do want to highlight sort of, again, some of the instrumentation that was needed to actually sort of enable this. One big component are the red optical spectrographs, sort of like NUID, or near-infrared spectrographs like HPF that really have increased the sensitivity to observing these M-dwarfs. In terms of visible magnitudes, most of the sample is V greater than 14.5, easily going down V of 17, 18. So it's a traditional sort of optical spectrograph. It's really difficult unless you have a large aperture instrument to even get the signal to noise to actually detect even a Jupiter, where your SEM amplitudes are anywhere from 70 to 100 meters per second. So in this case, we've really sort of leveraged, again, sort of these new instruments that recently came out to actually enable us to observe these objects, get their masses, and really constrain them and confirm them as genuine planets. The other big push for this survey has been TESS, again, launched in 2018. It's really sort of revolutionized what we can do with M-dwarfs. And I want to emphasize that the search for gas giants around M-dwarfs is not a new thing. So there was a WTS survey back in 2013. There's also the Pan-STARRS survey back in 2016 from Obermeyer in 2016, where they were actively looking for, again, gas giants orbiting M-dwarfs, but their sample sizes were maybe 20,000 stars. So with the occurrence rate that at least we've estimated from TESS of like 0.2%, I don't think any of those surveys actually found a genuine planet. But with TESS, we now have an opportunity to, again, study millions of them. And so even if they do have a low occurrence rate, we actively still detect them. And so part of this, to actually sort of develop this project, we needed to leverage some of the existing tools that were designed for Kepler and TESS. Particularly, again, we really want to search this 1 million sample. On the left, that's basically the 1 million subset that we have, that we've created from Gaia, that have been observed for TESS. So it's really is a dense number of stars, and even more so when you consider how many light years we actually have. Our goal was to develop something where we can take that photometry, search it and vet for it, and actually find something sort of like on the right, So this is Ki-254 or Kepler-45, and this is just chosen for reference. But these are going to be faint. So this is a TMAG of roughly 15. We were really probing for something that, again, had sensitivity to these faint objects, particularly because we wanted to go for more completeness around late M's. So these are, things that are less than 0.3 solar masses. We really wanted to sort of start to probe that region, see, do we also see these gas giants around the smallest of the M-dwarfs? So we have developed a pipeline. So this should be released with an upcoming paper from a graduate student that we're working with. So Rowan Busman, she's at the University of Amsterdam. And she's been really helping us sort of move on this program. But we've developed a pipeline to actually prepare photometry, perform a BLS search, and actually vet candidates. So this is just a little schematic. But again, because we're going for these faint objects that are not necessarily accessible through most high-level science products, we ended up just re-reducing the entire photometry available for the 1 million stars using test sky light curve. So test sky light curve, and that's point spread function photometry that is really sort of deblending and decrowding out sort of dilution from adjacent stars. In particular for this, our objects are faint, again, Tmags of anywhere from 13 to probably like 18. So we really needed something that could account for dilution. That's, again, TGLC taking advantage of Gaia, the Gaia information that we have available. We then had to consider how we could sort of detrend some of the photometry and sort of mask out things, especially at these faint magnitudes. And so that was a large work of figuring out something that could identify flares, that could identify regions of the test observation that were masked or just really bad, regions where you're dominated by sort of reflected light, regions where or scattered light, regions where you're dominated by background noise. So a bunch of things. And so in this particular example, we're actually cropping out a lot of the data that you see on the top row raw, just because that's where we have a lot of systematics, either from tests or just through the background that we're seeing with TGLC. The next thing we had to deal with was activity. So M-dwarfs are very active, famously so. And that's doubly so for, as we're probing down sort of faint M-dwarfs tests, you see activity all around. So we ended up sort of modifying a few public codes. In particular, the workhorse here is WOTAN. So we did a few modifications there to actually have something that was robust enough to reliably sort of remove any weird systematics that were potentially a part of TGLC itself, and also any intrinsic stellar variability. Analysis of our samples currently underway. So the pipeline, again, we have run some injection and recovery examples, tests just to see how well we recover things. On average, we're very sensitive, not too surprising, to things that are less than sort of 6 days. We recover roughly 85% of everything less than 5 days, which is comparable to what you expect for other works that have done this. So Ed Bryant and Chandran Gunn's work, similar recovery rates at periods less than 5 days. So for that, we were really happy. The recovery is less ideal for things, again, that are longer than 5 days. We are only looking at sector by sector analysis. The difficulty here is we didn't want to sort of join and stitch various sectors because they're different noise parameters, because they're from extended mission, prime mission. So we opted for this particular project to just look at individual sectors from individual surveys. So that's why we don't really have much sensitivity going further. But I will say that the work that Rowan's done is really promising. So we do recover everything that has been sort of announced as either a candidate through various community efforts or has been converted to planet within 100 parsecs. So we recover all the TOIs and all the confirmed planets. And in addition, we've recovered an additional sort of 14 candidates, of which I'm actually going to highlight one in a few slides where we actually confirm it. But it's been really, really nice to see that when you consider a larger sample, a larger, more complete sample, you still recover this. So it's showing, I think there's still potential in tests to sort of really make headway through the sample and find more planets that we can then characterize in detail. I do now want to briefly shift gears to talk about stellar obliquity. And in particular this, again, so as I mentioned with the test project, that's designed to really sort of find these objects, characterize them, get in a sense for what their orbital parameters are, mass, radius, etc. Another probe for information is stellar obliquity. And so there are many works, Rice et al. 2022, Albrecht et al. 2021, that come to mind that really sort of detail all the work that's done with stellar obliquity around sort of hot Jupiters and warm Jupiters. And particularly, we, through various studies, have a sense that hot Jupiters form dynamically through sort of chaotic migration pathways, whereas warm Jupiters don't appear to do so. It's more difficult to say anything about M-dwarfs because we only have one obliquity measurement to date, so that's 2I4201. But we really want to leverage, again, these sort of new instruments, in particular in this case, Maroon X, to sort of make this measurement. So observe these planets in transit to see is there any radial velocity RV anomaly, which is shown here on bottom, that might be indicative that our planets are either sort of aligned or misaligned. And so we do have a program with Maroon X in 2025A, where we're measuring the obliquity of 4 gems that are spanning sort of mid-M dwarfs to sort of early M dwarfs. Again, here I'm highlighting all the obliquity measurements that we know to date for FGK dwarfs that are just clustered as sun-like stars, yellow in this image. And I'm highlighting the one measurement that we have from an M-dwarf, so that's 2I4201, that's gone at all 2024. We really want to sort of expand this down to lower mass stars and just really, again, out of the 30 samples, we ideally want to have more, just to say, are they all well aligned? In which case, but again, it would be more similar to the warm Jupiters, or is there something similar to what we see with hotter stars, where there's some that are polar, some that are aligned? It's sort of difficult to know what to expect right now, again, given that we only have one sample. And I do want to emphasize that these are all systems that are very well separated from their stars. So think A over R star of 10 plus. And this is really sort of an opportunity to look at a subset of gas giants that are tidally, not really engaged tidally with the star. And so we're really hoping that we can start to probe obliquities with this coming program. And I do want to highlight this target. So this is one that was found through a VLS survey. This is TIC 459. It's in TESS, so we see it. It's a really deep transit. So, again, I think I mentioned before, you have giant signal around these gems hosting stars because these are Jupiter-sized objects around very small stars. In particular, this one's a Jupiter-sized object around a 0.34 solar radius star. And so that's why you have a very deep transit of like 15%. It really popped out in tests. Ground-based instrument, we've made detections with a small 300 millimeter telescope of this actual transit. So it's really great, really deep. We use HPF to actually confirm it. So we know that its mass is roughly 0.7 Jupiter masses. So it is one of the more massive objects. And in particular, the really deep transit makes it ideal for in-transit surveys, in-transit observations. RP of our star here is like 0.35. So it's 35% of its whole star. And we just got data for this object in transit with Maroon X on Saturday. So I was hopeful that it would have been observed earlier and I'd have data for you guys, but unfortunately not. But we're actively in the process of validating. So it'll be a paper where we're showing all the RVs while doing an obliquity measurement. So that'll be the first obliquity of one of these M-dwarfs orbiting a mid-M dwarfs with a gem. So again, if you look at it in terms of the known gem population, it's the little star on the left. So it's the most massive one around sort of ours mid-M dwarf population there. So we're really excited that we've managed to confirm this. And now that we have, at least we have data from Maroon X, where this should be either a whopping signal either way, because again, it's 35% of the stellar radius. So from this perspective, we're really excited. This is the first analysis from this ARM project that's going to come out. And so myself and Shubham will be leading this paper where we're actively working on it. So look forward to sort of results from this. We have 3 other observations that are coming from anywhere from June or from May through, so end of May, so end of this month, through July. So expect some other, again, results from this survey. And we've also requested additional time in the upcoming semester to sort of complement this and start to look at some of the other systems. But I think, again, these instruments are really starting to sort of let us probe these systems, and we're really excited to see what we find. With that, I do want to move on to sort of the biggest component of this, and this is sort of the atmospheric constraints we get with JWST. As I mentioned before, this is a huge collaboration. So this is in particular the GEMS JWST collaboration. There's a QR code if you want to follow it and see sort of just all of the details about the people and the planets that we're actually doing. So this is JWST cycle 2 GO 3171. So its PI is Shubham Kanoya, myself, and Jessica Libby Roberts. So we're the three on the left. And we're sort of leading a group of roughly 28 sort of researchers. A lot of them are early career researchers that we've really wanted them to take the forefront in JWST, learn how to analyze the data, learn how all the reduction tools, all the data analysis tools. And it's been a really wonderful collaboration to work with. And so again, when I'm presenting these results, it's not just me. It really is a group effort through all these people here. So our program is designed to observe 7 of these gems. So we have already observed 7 of them, 18 transits. So we have a lot of data. All these are near spec prisms. So we're observing 0.6 to 6 or 0.6 to 5.5 microns. On the left is a plot showing sort of, well, I guess both these are plots showing schematics in terms of planet mass and sort of planet radius, but also stellar mass. Just to give you context, we try to span the bulk of the population that we currently have. So going from mid-M-dwarfs, our coolest one being TOI 5205, all the way to early M-dwarfs, with the hottest one being something like TOI 3757. We've also tried to really cover the mass axis. So our least massive objects, TOI 394, and that's, I think, 0.18 Jupiter masses. And then, of course, we go towards the more massive end, TOI 5205, which is 1 Jupiter mass. So we really wanted to cover at the time when we did this for cycle 2, just the extreme ends of both, just so we can really get a sense for, in this population, how do they change as a function of stellar mass, planetary mass, radius, etc. In particular, we were interested in sort of 2 questions, one of which, is there a mass atmospheric abundance trend? And so this has been work done by initially Luis Banks in 2019, using the HST survey of hot Jupiters, and more recently, sort of again reanalyzed by Sentinel in 2024. In the solar system, so that's the top orange, we tend to see a inverse trend with planet mass and methane abundance in the atmosphere. And that's long been thought to be sort of an implication that core accretion is at play, and that's why you're getting this sort of inverse trend. With HST, there was potentially a tenuous trend with water. So with HST, these are hot Jupiters. You don't actually have methane in the atmosphere. You can't make comparable methane abundance measurements. So they use water as sort of another proxy to, again, say what's the metallicity in the atmosphere. Tentatively, there was this inverse trend. And we were interested, well, with these gems, they're in that regime of, again, say 600, 700 Kelvin, where you can actually make measurements of both water and methane. And so we were interested, do we see any trend in any of these elements in the atmospheres of these gas giants? And our sample actually covers a huge span of this. Again, we're going all the way up to Jupiter. We're also going down to 0.2 Jupiter masses. So we were interested in one case, is there any evidence in either methane or water that we see an inverse trend, which again might be indicative of core accretion being at play, or at least them forming similar to how we see in the solar system. We were also interested in, is there a mass bulk metallicity trend? And particularly here, again, a negative correlation between mass and sort of heavy element abundance in gas giants has been seen as something indicative of, again, core accretion being at play. And this is particularly from Dornberg et al. 2016. But in this case, we were interested in using measurements that we get from JWST, so atmospheric abundances, basically the Z that we get from the atmosphere, as a constraint for modeling our interior. So ideally, we want to use our atmospheric abundances plus planet cooling tracks for these gas giants to really get a sense for what is the bulk metallicity enrichment in these planets, and how does it compare to what we see in the sample of hot Jupiters, and of course in the sample from the solar system. And those are sort of our 2 motivating things, again, to really go back to the main question of how do these objects form, and what can we really glean from sort of their atmospheres in terms of is core accretion, gravitational stability, etc. I do want to emphasize that our observations really showed a lot of things, let's say. And one of the biggest things here are star spots. So we see a lot of intrinsic variation due to star spots. It's visible in this. So this is TOI 5205. These are just showing the first 2 transits. You see morphology of that sort of intrinsic signal change as a function of time. We also see it in a lot of our gems. So out of the 7 targets, 6 have intrinsic crossing events. And yeah, you can't really get away without modeling it. just because JWST has amazing precision, so it beats anything you have from the ground. I will say that when we targeted this object based off of test and ground-based data, we had no idea there were spot crossing events, so there was nothing in test that indicated variability. And nothing in our spectra either, so we thought it was the perfect object to start with. And JWST surprised us with all of this. When you look at the three of them, these are the three transits GL5, GL5. So again, for context, this is the one Jupiter mass, one Jupiter radius object around M4. There, at least in the modeling that we've done, there has to be a lot of sort of evolution of the spots that actually cross the transit port. So on the top are the three sort of individual visits that we see from JWST. On the bottom is our best fitting sort of model of spots. Again, in this case, we did a joint model for all three. We allowed each transit to vary in number of spots from anywhere from 0 to 5 spots. And this was the one that sort of best fit the data without sort of overfitting, we'll say. So we looked at BIC, AIC, et cetera, and this was our best configuration we came up with. 2, 3, 4 spots. A lot going on. And I also want to say that these are consecutive transits. So these are back to back to back. So there's must be a lot of evolution in the system for it to actually change in terms of where the bumps that we see in transit are. And again, this is one current sort of iteration you can have. I will note that you can have a few different sort of configurations in terms of spots, just because there's degeneracy here. When we're fitting the white light curve, you can have degeneracies in the axis. We don't actually know the obliquity. We don't know the rotation period. So there's an additional degeneracy there. But needless to say, these systems, particularly this one, is fairly active. But again, with the beauty of JWST and its precision, we're actually able to sort of measure this, measure where the spots are, get a sense for the contrast, which for reference is these spots, while they look large, so anywhere from like 0.1 to almost 3 times the radius of the star, they're not that hot. So the contrast in terms of temperature for these objects, for these spots, are like 150 to 200 Kelvin. So they might be large, but they're not actually really dark. So very different from what we see in the sun, where you see these dark spots. The delta T in terms of the spot in the photosphere is not too significant. And for reference in terms of flux ratio, so the flux ratio of the spot to the flux ratio of the photosphere, it's like hovering around 0.89 to like 0.92. So again, they're not really dark spots, but they tend to be huge. And I do want to emphasize again, because we have such high signal to noise, you can't actually ignore this when generating your transition spectrum. You see it on individual channels, and what I mean in channels, if you take the near specs prism data and you just look at one column, on the blue end you will see clear distortions due to spot. And so if you actually want to have sort of a more robust transition spectrum, you really do need to account for spot crossing events. And so in this program, we leverage sort of tools that have been in the community. So particularly SpotRod has been sort of our main modeler for this particular system, but we have looked at other sort of tools like Starry, as well as FLEC. So if you have any questions about those, I'm happy to talk sort of some of the details. I will note that out of all of them, just because of the amount of data we had and the complexity of the model, SpotRod was sort of the easiest to work with. But again, if you have questions, I'm happy to address them later. Now, I just discussed that we did have spot crossing events. I also want to say we expect the transit light source effect. And so we see spots in the transit port. We see them being occulted by the planet. Naturally, we aren't expecting spots to be just at the latitude that we see our planet cross. So we're also expecting unocculted spots in our star. And this is a schematic of that effect from Racket Model 2018, where if you have unocculted spots, then you should have basically on the blue end, a ramp. So if they are genuine spots, the transit will be sort of deeper. And so you'll see this blue ramp as you go towards the blue end, and your transit will basically go up. And when we look at TI-5 205 in terms of the individual transits, we actually do see that. So we do see a significant TLS effect in addition to spot crossing events. And so when taken together, again, suggesting that this star is particularly active, has spots all over its surface. And that sort of proved a challenge to actually sort of modeling this, just because we, again, now have to contend with also having stellar contamination in our actual spectrum. I will note, and I will at least positively note, that the spectrum cannot just be stellar contamination. So this is a co-added spectrum, 2.525. So we took the previous 3 visits and took the median of them, and we ended up getting the spectrum. If you model this with your favorite tool, in this case Poseidon, but you can also get similar results with Platon, Characterize, etc. We see that you cannot actually recover the observed spectrum purely with stellar contamination, and so that's what we're showing on the sort of red here. So that's our TLS only component. If you assume your planet has no atmosphere for whatever reason, or just if you just ignore the planet and you say, can you model this with stellar contamination? You can. It fits really well in the blend, and so we naturally expect that most of the water features we're seeing are due to contamination with the star. And so most of the water features that appear to be water features are actually sort of features from, say, star spots. And again, that blue ramp on the left is what we're attributing to, again, these sort of unocculted spots. But really, once you start getting sort of redward, and particularly beyond like 2.5 microns, you really start to see features that can't be purely expressed with a stellar spectrum. And I will emphasize that we tried this with various different sort of stellar spectra. This result is for Phoenix, but we also looked at Sphinx and a few other sort of model grids. Nothing actually, again, can model any of the other sort of features that you see redwards of 2.5 microns. And so we were confident in this, at least greater than 5 sigma, that TI 5205 cannot be purely sort of modeled as just stellar contamination. Here I'm highlighting sort of the final model where we added a bunch of other sort of molecules that we expect. And we were really interested in seeing what do we actually detect. And in this particular spectrum, the dominant molecules that you're recovering are methane. So that's that feature that's roughly from 3 to 4 microns. It's that yellow peak right there. We're also getting hydrogen sulfide, and that's sort of the purple features you see. Some of it is 3.5 to like 4.5 microns. And of course, the TLS. Interestingly enough, we never recover water. We also never recover any oxygen-bearing molecules. So we see no CO, we see no CO2, no water, no SO2. We don't actually recover in the system anything that has oxygen. And I do want to note that because we have a strong TLS component, there's some degeneracy there with the sort of water abundance, but we certainly don't expect TLS to mask any CO, CO2, or anything redwards of 3 microns. So when we started to initially look at this, we were sort of perplexed because it was really looking like something that is metal poor. In this case, if you actually forward model this with Picasso or Platon, you really tend to run up to the lower metallicity bound on that grid. So from those grids, we're getting atmospheric metallicity of -1 or -2 index. And C-to-O ratios were also sort of hitting the upper limits of those grids at like 1. But because we actually used Poseidon, we were able to recover sort of a bit more robust constraints. And sort of here, I'm sort of showing the retrieve parameters, again, are suggesting that we have something that's a high atmospheric C-to-O, but also low metallicity. And this is without clouds. I'll get into the sort of caveat in a bit. But on the left, sort of we're showing a bunch of the retrievals we ran with Poseidon, with Platon, and well, Poseidon and Platon chemical equilibrium, and Poseidon free retrieval. So we're not assuming chemical equilibrium. We're just letting the abundances float from -10 to 10 wild abundance. As you can see on the left, when you look at Poseidon or Platon, assuming chemical equilibrium, no matter the grid you're using, you'll always run up to a sort of tail that sort of explains that sharp cliff we have on the left end. None of those were great fits. And they also, again, hit the lower bound of metallicity. If you let it float, you see that we're getting metallicity of roughly -2.5-ish. So really, really metal poor. And also metallicity of roughly log C-to-O of 3. And again, this was consistent with what we were seeing going back to the spectrum. This was consistent with what we were seeing in our spectra, where again, we weren't actually recovering any water, any CO2, anything oxygen-bearing species. We were just recovering methane, hydrogen sulfide, and TLS. There is a caveat that I mentioned of clouds. And for this particular system, because there's so much going on in terms of the translysers effect, when you add additional clouds, there's some instances where you recover really unphysical parameters. And so you might have a very high level cloud, but a very hot photosphere or hot atmosphere. So we're talking easily temperatures of 1500 Kelvin, but a cloud deck that's really high up. which is unphysical for the equilibrium temperature we're expecting for this particular system, which again is roughly 750 Kelvin. There is a solution where if you add clouds and you look at individual visits, you can potentially recover something that's slightly more metal rich, but we're not. It's not shifting it really to any high metallicities. So that would be at probably -1. We're still broadly looking like it's pseudo rich. Again, that's really dependent on the methane that we see, the methane abundance we actually recover, and also metal core. And I do want to emphasize that this particular system will be observed in cycle 4. So we are getting 2 observations with MIRI, not of the transmission spectrum, but the emission spectrum. And so our attempt here is really to look at our transit light source effect. So go back to this plot. We really want to try and confirm that there is no water in this atmosphere. And that's where the emission spectrum comes into play, where we can reliably make a detailed measurement of water in the atmosphere using a thermal emission image of this planet. Again, this is short period, 750 Kelvin around M4. And so it really does have an optimal sort of flux ratio where in MIRI, you can actually detect the secondary eclipse and then model that to really get a sense for if we don't have this sort of complexity of the transit light source effect, do we equally recover no water? And that's just, again, confirming really our constraints that you can say with transmission, with our current limitations of the models, of the stellar models, and our current limitations sort of the flexibility of the TLS effect. Actually, we're really excited for that because it's going to serve as sort of like you can think of it as a sort of confirmation, or I guess it'll tell us and calibrate how well we correct currently for the transit light source effect in the spectrum. And I do want to emphasize that this is, again, not the only planet. Well, before I get to that summary, I want to emphasize this is not the only planet in our survey. So this is one of 6. Currently, we are working on the other 6 manuscripts. So 3 should be out by summer. So that would be HATSELF 6, TY 3714, and TY 3629. Yeah, sorry. 3714, HATSELF 6, and TY 3714. All these numbers blend at a certain point. But we're looking at a Saturn, we're looking at a Jupiter, and we're looking at a low density subsaturn, basically. So those 3 should be out soon. I will say, I don't want to necessarily, well, I won't spoil it, but they're all sort of looking similar to this in that we don't really recover anything that's really metal rich in all these systems. So it might just be that this population is, that's just how these gems are. The goal of this survey is that once we have everything out, we'll actually do an analysis on these parameters and actually have a sense for relative to hot Jupiters, relative to what we know. How do these planets compare in terms of, again, atmospheric properties? But do look forward to those systems in the coming months. I will sort of flash up my summary slide and emphasize again that at least TESS, JWST, and next generation instruments have really sort of enabled new observations into GEMS. And so TESS enabling sort of a survey to find these in photometry, so actually find them. Then with ground-based instruments, we can measure masses, we can measure eccentricities, look for additional companions, look for obliquities, and of course, JWST, we can then actually probe the atmospheres. So it's really an exciting time to understand these planets. From TESS, the BLS search, the 100 parsec sample, that is underway, and we're expecting to have that paper out sometime in August. So look forward to a paper from Glossman et al. 2025. We'll should be presenting sort of our work there and the results of the 100 parsec search, what planets we found, what additional candidates we found, and sort of next steps towards really doing the whole 1 million samples, so 200 parsecs. MaroonX, the program is underway. We already have 1 observation of an obliquity. That's, again, the object I showed earlier, T459. That'll be out at some point this year, as I have time. But we are getting more data. And so do look forward to at least having more than 1 obliquity for a gem. So it'll at least go and give us a sense for if TI4201 is comparable to the rest of the population. And again, for JWST, our program finished observing, but we are currently doing a lot of analysis. And so, again, if you want to go into specifics, I'm happy to chat. We are looking, in addition to spot crossing events, there's potentially some limb asymmetries. So we're looking at that as well for planets that don't have spot crossing events. we're looking for, again, really 5205 is the only one where we have these sort of measurements really robustly measured. Tentatively, other systems are looking very similar, that low metallicities, but also high C to O ratios. I think all of them show methane, and maybe one shows a slight CO2 feature, but by and large, they are all methane is the dominant thing we recover. So high C to O, low metallicities. But again, I'm happy to chat later in the week. I'll be around. That's all I have.
Any questions in the room?
Hey, Caleb, great talk. I know this is a loaded question because M-dwarfs are hard in a general sense, but can you say something about the host stars for these JWST targets? Do you expect, are they also metal poor? Do you know?
So-
what are their ages?
Yeah, so ages are a bit difficult. None of
Yes.
these are particularly young. So at least in terms of like spectra or test ground-based photometry, for the ones we do have rotation periods, they're 20 to like 50 days. So they're not particularly young systems. We don't see any signs of flaring in tests. We don't see any significant broadening in HPF or new spectrum. By and large, just based off of all those parameters. In the discovery papers, we've all aged them to roughly 1 to like 60 years. They're not young, but they're also not, it's unclear how old they are, I guess. The bulk we can say is that they're not young. Some of these we knew going in, so at least 2 of them, 3 of them, we had rotation periods clearly measured from the ground with ZTF, so we knew they had activity cycles. I will say that these activity cycles are on the longer side, so again, 23 days was our shortest rotation period that we have measured, 50 days is the longest one. But the activity that we're seeing for JWST shows a lot of evolution, particularly for the 50-day one, that's TLI 3984. We have 3 visits, of which the first 2 are separated by like 30 days and basically look the same. The next one, which was obtained right after, it is completely different. With like, you need basically 4 spot crossing events to actually model the transit variability. So I guess we weren't surprised at how rapid the evolution is, right? We have some sense of the rotation period, but yeah, in future, I think we definitely would have wanted to sort of pad it with some sort of ground-based high resolution spectrum to actually have a more robust way of measuring like spot coverage fractions. Just because at the resolution we're dealing with Prism, like 100, you can't do too much in terms of modeling the actual sort of stellar spectrum. No problem.
For people online, if you have questions, please raise your hand or just type them in the chat. Adrian?
Really excellent talk, really excellent work. I was just wondering how you thought that, is that a negative 2.5 or?
Yeah.
Okay, yeah. So how do you make a super low metallicity carbon planet? Is it like dry conditions, creating gas? I was wondering how.
Yeah, I guess that's a question we've normally punted for at the end of the survey when we have sort of measures from everyone, just to see if like this is an outlier. But no, that's a question, and it's actually, so I didn't go into the detail here, but I mentioned bulk metallicity as well. So for 20525, if you look at bulk metallicity and just look at mass radius and what you expect, you sort of need a Z of like 0.15, which is very different from the Z we're measuring in the atmosphere. Up again, minus like 3 was I think the average. So we were a bit puzzled there as well, because it would suggest there's basically no mixing in this particular system. Yeah, it's formation-wise, again, at least for the purposes of this paper, we haven't given it too much thought. We just noted it there. But yeah, it's a perplexing thing of how do you have a Z of minus 2.5 and then form these objects. And I think quickly going back to your question, Sarah, you asked if the whole stars were metal rich. Yes, these are all. So Tianjun Gan et al. 2025 did a spec survey of I think all of these objects. I found that the metallicities are at least 0.2, like anywhere from 0.25 to like 0.5. So all the host stars in themselves are actually metal rich, which at least is in line with the planet metallicity correlation that we see. The Fisher et al. 2024 or 2004. But yeah, that was our one sort of, these are interesting systems. And once we have more measurements from the rest, I think then we'll probably start to probe that question of how do you actually what mechanisms do you need to actually form these objects?
Great talk, Caleb. On the in one of the slides, you show several of the gems and the planet mass versus radius. And some of them, they were apparently by the names, were binaries, that one.
Yes.
Those are observed with JWST and to right is are part of the program. And what challenges add the fact that they're in a multiple system. And I have another question.
So I did ignore this. So out of our sample, we do have 3714 is also a binary, so it has a electron companion. But they're all well separated, at least the distance. In terms of AU, the closest one is 400 AU, so it's really far out
Right.
from what JWST would actually observe. But yeah, this sample of 7, TY 3714 has a white dwarf companion, as this TY 3984, which has a white dwarf companion. 3714's the distance of that companion is I think 400 AU. For 3984, it's like 600 AU. 5293 has an M-dwarf companion that's at like I think 700 AU, something like that. So they're all at least well separated that from the perspective of JWST, you wouldn't actually expect them in your spectrum.
And the other question was related to but when you model the spots from the observations, and I was wondering, you mentioned something about the rotation period. I'm not quite sure if I missed something. Right, so you use prior knowledge about the rotation period to model the
For this one,
spot,
unfortunately-
or backwards, like
Yeah.
you can get or can you get a rotation?
So that's one of the sort of ancillary things we're trying to do is, can we look at rotation rates for things that we don't have a sense, especially if, again, in this case, they're consecutive transits, you see evolution of spots. Ostensibly, they're the same spots, hopefully. For some systems, it's a lot easier, I think for HATSAL 75, which is our last object observed, you clearly see like the same spot moving as a function of time. They're consecutive and it's actually really nice. It's like a picture book spot. You're just seeing it move along the study board. For this one, we didn't have that information. So we modeled it without any constraint on the actual rotation period. And again, that's why we really leverage spot rod, just because spot rod doesn't take into account rotation periods. That's something you would add for Fleck or starring. But in this case, that's sort of the tool we opted for because again, we had no information. But there is an ancillary project that we're hoping, can we tease out rotation rates for those where we know the rotation period? Can we look at obliquity? I think it's a separate project we'd like to do.
Yeah, well, thank you very much. This is very interesting, and I have many questions, so I hope we can discuss after I sign up. So here I just wanted to make a comment that I understand that there are these challenges in retrieving the abundance of water you mentioned, like the spots, the clouds, but potentially if you find that really there is a high carbon to oxygen ratio in this atmosphere, it's very interesting because it connects directly to protoplanetary disks, where we found that around M-dwarfs, inside the snow line, actually the carbon to oxygen ratio is very high. And you have a lot of hydrocarbons, so that's quite interesting.
I think
we should talk more.
Yes, we should. I saw a talk from some of the JWST, I think, disk groups. And
yeah, but it was discovered already. We discovered with Spitzer already, so it's just confirming that.
Yeah,
so
no,
that's really interesting. Yeah.
That would be interesting. And again, I think in all of these we are at least, so 525 we're definitely covering high CETO. For the others, we're again getting very comparable results. We'll have more robust measurements once the sort of analysis is actually done. But yeah, we're actively seeing how we can sort of use, again, measurements from disks to sort of complement this. You know, maybe that's just how M-dwarf planets are, and that might explain it. But yeah, we should definitely chat after.
Yeah.
Andrew, do you want to ask your question?
Yeah, thanks. Really nice work. So I guess, yeah, I mean, commenting on the sort of the general idea that sort of, you know, rare objects like giant planets around M-dwarfs might be a challenge to theory. I mean, one perspective is that, well, if the theory says they're rare and they are somewhat rare, that's maybe a success of the theory. And so on that, I appreciate you just mentioning the Ganadol work, that the hosts appear at maybe the 3 to 4 sigma level to be metal rich. That's interesting. What I also wanted to ask about, though, was, and sorry if I missed this, was the bulk densities of these planets, and whether these are hot, whether these are truly hot Jupiters or just warm Jupiters, where you can use the bulk densities for the to say what the overall planet metallicity is.
Yeah, so excluding 5205, the remainder of our planets are, I think, all within 2 sigma of like the density of Saturn. I don't have unfortunately, I don't have a plot here of the density. But in terms of radius, they all, so again, here's on the right sort of is the plot of the mass radius. They are all generally roughly hovering around, again, 5205, just for calibration, is effectively one Jupiter radii. So they're all roughly around, most of them at least, are around 1 Jupiter radii. We have, again, Hatzal 75, slightly smaller, and then TI 394, which is the smallest one at roughly 8 Earth radii. None of them were anomalously large, although TI 3757 is our sort of very low mass. And in that one, at least in the discovery paper, we were curious if there's sort of tidal inflation going on, because its density for that particular one is like 0.28 grams per centimeter cube. Everything else is larger than that. Hopefully that answers your question.
Yeah. No, interesting. Yeah, sorry. Yeah. So thanks for showing this again. Yeah, no, it looks like most of the equilibrium temperatures are below 1400 or so, which is where you usually see strong inflation. So,
Oh yeah, the hottest one we have is 750 Kelvin, and the coolest one is like, I think, 650, if I recall.
thanks.
Ask a maybe naive question.
Sure.
How the sample of these 7 planets are selected? Because based on this plot, it seems like most of them are like clumped together at the center, while there is one outlier in the border.
Yes, so how we chose these was a few things. One, we wanted to look at what precision we could JWST. So there isn't really information on brightness here, but a few of these are J of like 13 or something, where even with 3 visits with JWST, you wouldn't actually really reliably, robustly measure the transition spectrum. So a big subset of this was sort of simulating what we expected. So in this case, we assumed some nominal atmospheric abundances and simulated with Pendexa, the atmosphere, the spectrum we'd get to see what precision. Once we have the spectrum, we modeled that spectrum to really get what precision we'd roughly expect from JWST. And sort of we opted for everything that's sort of in the middle was mostly signal to noise, and then we forced TI 3984 and TI 5205 as sort of the 2 interesting objects, in that TI 3984 was our lowest mass gem known at the time. And then TI 5205 was the one around the coolest whole star. So that's why those 2 are included. Everything else was looking at signal to noise and what we can realistically recover. Some of them are overlapping, and we ignored the ones that are nearby just because those were fainter. So another one that could have been chosen here was Kepler 45, but again, that's J of 13.5 or something. Whereas these are ranging from J of like 11.5 to 12. So it was a combination of, again, sort of expected precision you'd get, and really trying to optimize the mass coverage and the stellar mass coverage.
Other questions? Any other questions from the online audience? If no, we thank our speakers.